The most dangerous control room graphic is not the one that looks outdated. It is the one that looks convincing while telling the operator an incomplete, ambiguous, or false story about the plant. You may have a technically correct piping and instrumentation diagram, a fully configured distributed control system, thousands of tested input and output points, and a polished human-machine interface. Yet the operating system can still fail at the exact point where human judgment meets process reality. That failure begins when you treat the process display as decoration. A process display is not artwork, and it is not a digital copy of a piping and instrumentation diagram. It is an operating decision surface. It must help the operator perceive what is happening, understand why it is happening, decide what must be done, and act before the process moves beyond safe or recoverable limits. The operator should spend mental capacity understanding the process, not decoding your display. That single principle should govern symbols, colors, equipment states, alarms, navigation, control modes, data quality, communication failures, and fallback arrangements. When every vendor, package supplier, engineer, and project contractor introduces a different visual language, the control room becomes an interpretation problem. One screen uses green for running, another uses green for available, another uses it for healthy communication, and another uses it for an open valve. Red may mean stopped, closed, tripped, emergency, or simply selected. A filled valve may mean open in one unit and closed in another. A dashed line may indicate software communication, an electrical signal, or an unavailable connection depending on who drew the graphic. That is not flexibility. It is unmanaged ambiguity. During normal operation, experienced operators may compensate through memory. During startup, shutdown, equipment failure, or process upset, the weakness becomes visible. The operator must stop, interpret, and verify before acting while the plant continues to move. Standardization exists to eliminate that unnecessary cognitive load. The process display system should create one coherent language across equipment, process flow, instrumentation, shared control, logic, alarms, and computer functions. It should allow the process engineer, control engineer, operator, and maintenance technician to look at the same symbol and derive the same meaning. A pump symbol should identify a pump, but it should not pretend to tell you everything about the pump. The display must separately communicate whether it is running, stopped, starting, stopping, tripped, unavailable, in local control, in remote control, under maintenance, or suffering from failed feedback. A controller symbol should not merely tell you that control exists. It should clarify whether the function is accessible to the operator, hidden inside the system, executed through a shared controller, supported by an analog backup, or dependent on a supervisory computer. A process vessel may be represented simply, but the process story cannot be simplified into something false. The symbol may omit construction detail, but the display must preserve the actual operating relationships, major flow paths, bypasses, recycles, utilities, and critical isolation arrangements. You can simplify the appearance. You cannot simplify the truth. This is where many projects go wrong. They begin with a piping and instrumentation diagram and attempt to fit the whole drawing onto a monitor. Every valve, reducer, drain, vent, line number, and instrument bubble is transferred because it already exists in the engineering document. The result may be technically complete and operationally useless. The operator does not need to continuously see every engineering detail. The operator needs to know what is running, what is stopped, what is available, what is abnormal, where material is flowing, which variable is approaching a limit, which controller is responding which path is blocked, and whether the displayed information can be trusted. Maximum information does not create maximum understanding. It often creates engineering camouflage, where everything is visible but nothing is prominent. A strong process display separates static structure from dynamic behavior. Equipment, lines, and permanent labels provide context. Measurements, equipment states, alarms, control modes, sequence steps, and communication quality reveal what the plant is doing now. Dynamic information must be easier to find than static artwork. A beautifully rendered vessel must never compete visually with rising pressure. A three-dimensional pump must never overpower its trip state. Decorative animation must never distract from a failing process variable. Normal operation should appear calm. Abnormality should create contrast. That is why color must be treated as a controlled coding tool rather than decoration. When everything is colorful, nothing has priority. If running equipment, process lines, controller modes, navigation buttons, and decorative backgrounds all use intense colors, the display has no visual capacity left when a real abnormal condition appears. Define a project-wide color philosophy before graphic production begins. Decide how the interface will represent emergencies, warnings, normal operation, unavailable equipment, maintenance, inhibited alarms, bypassed protection, bad quality, stale data, forced values, simulation, and communication failure. Never allow each package supplier to bring its own color vocabulary into the control room. The operator should not need to remember which vendor designed each screen before interpreting its meaning. Color should also never be the only carrier of critical information. People perceive color differently. Displays may be viewed under poor lighting, through remote systems, on low-quality monitors, or in monochrome documentation. Meaning should survive the loss of color through text, shape, fill, position, border treatment, or another redundant cue. The same discipline applies to blinking, reverse video, and high-intensity highlighting. These are scarce attention resources. One blinking object attracts attention. 20 blinking objects create noise. If everything demands attention, nothing directs attention. Equipment state must be equally disciplined. Commanded state is not actual state. A start command does not prove that a motor is running. An open command does not prove that a valve has opened. A breaker close command does not prove electrical continuity. Where feedback exists, the displayed state should be based on feedback. Where a command is issued and the expected state is not confirmed, the operator must see the transition, mismatch, or failure condition. A valve may be open, closed, opening, closing, intermediate, failed to open, failed to close, locally controlled, manually positioned, unavailable, or unknown. A motor may be running, stopped and available, stopped and unavailable, starting, stopping, tripped, interlocked, or under maintenance. You do not need to show every state permanently on the primary display, but you must engineer how each relevant state will be represented. Otherwise, the graphic configurator will make those decisions during implementation, and the plant will inherit them for decades. Data quality is another area where attractive graphics can become operationally dangerous. A value is not useful merely because it is visible. The operator must know whether it can be trusted. A measurement may be good, bad, uncertain, stale, forced, substituted, simulated, out of range, or calculated from failed inputs. A communication failure may freeze the last good value on the display. If that number continues to look live and valid, the display is presenting outdated information with the authority of current process reality. Imagine a tank level frozen at 52% while the real level has climbed above 90%. The instrumentation failure created the problem, but the display design allowed the problem to hide. Invalid data must never look valid. This principle should be tested deliberately. During factory acceptance testing, fail the transmitter, break the communication link, remove one feedback signal, reject a remote set point, trip the pump, prevent the valve from moving, put the controller in manual, transfer to backup, force an output, inhibit an alarm, simulate stale data. Then ask whether the operator can still understand what is real, what has failed, and what action remains available. Testing only normal operation is the easiest possible test. The quality of the interface is revealed when the system degrades. Fallback design deserves the same scrutiny. A drawing may show a backup controller, auxiliary station, redundant processor, or manual control path, but the existence of a symbol does not prove operational resilience. You must know what happens when the primary operator station fails, when the controller fails, when the communication link is lost, when the supervisory computer stops sending the remote set point, and when control transfers to the backup. Does the backup track the primary output before transfer? Will the transfer create a process bump? Can the operator identify that the transfer occurred? Can the operator still see the necessary process variables? Can the operator return the system to normal without confusion? A redundant controller pair may protect against processor failure while remaining vulnerable to common power loss, shared input and output failure, network failure, bad software, bad field measurement, or final control element failure. Redundancy is not the same as independence, and backup is not the same as seamless continuity. A fallback strategy is not complete until people can recognize, operate, test, and recover it. Display hierarchy is equally important because not every screen should carry the same amount of detail. The highest level overview should tell the operator whether the plant is healthy, which area is abnormal, where production is constrained, and which major equipment is unavailable. The process area display should explain major flows, equipment relationships, key measurements, and significant control loops. The equipment or control detail display should expose controller modes, valve states, permissives, interlocks, sequence status, and diagnostic information. Engineering and maintenance screens may then provide raw input and output status, device diagnostics, detailed logic, communication health, overrides, and configuration information. When every screen becomes a detail screen, hierarchy disappears and the operator is forced to search. Good design uses progressive disclosure. The main display reveals what requires attention. The next level explains the problem. The detail level supports diagnosis and action. The operator should not need source code to discover why a machine will not start. At the same time, the overview should not be covered with 30 tiny permissive indicators beside every motor. Show the operating condition first, then allow the operator to open the reason. Control system symbols must also distinguish accessibility and function. A shared display, a shared controller, a computer function, an internal calculation, and a logic function do not communicate the same thing. Modern control systems execute many functions in software. One processor may regulate hundreds of loops, run sequences, calculate derived values, and generate alarms. One operator station may display thousands of variables. Drawing every function as a dedicated physical instrument creates a false architecture. Drawing the entire control system as one box destroys functional understanding. Represent enough architecture to explain the control strategy, system boundary, operator accessibility, backup relationship, and critical dependency. Do not draw technology merely because it exists. Communication links should be shown when they clarify package interfaces, remote input and output, supervisory control, backup relationships, or important data dependencies. Drawing every network path creates spaghetti. Hiding every system boundary creates false simplicity. Show architecture where architecture affects understanding, failure, or responsibility. The symbol library itself must be governed as an engineered asset. Every reusable object should have a controlled identity, defined geometry, connection points, dynamic states, alarm behavior, failure behavior, interaction rules, and version history. A pump object should not be copied from another unit, detached from the approved library, and modified because one screen designer prefers a different color or animation. A change to a standard valve object may affect hundreds of displays. A change to state logic may alter operator interpretation across the plant. These are controlled engineering changes, not casual graphic edits. The lead engineer must therefore treat the human-machine interface philosophy as a project design deliverable. The project needs approved rules for symbols, process flow orientation, color semantics, display hierarchy, alarm presentation, data quality, command and feedback, backup control, package integration, navigation, and change management. The process engineer must verify that simplification preserves the correct operating story. The instrumentation and control engineer must govern functional identification, controller representation, alarm identity, system architecture, device states, and data quality behavior. The electrical engineer must verify breaker, motor, and power availability states. The package engineer must prevent supplier-specific conventions from entering the plant uncontrolled. Operations must validate whether the screen supports startup, shutdown, upset response, and troubleshooting. Maintenance must challenge the design with failed feedback, bad transmitters, communication loss, local operation, bypasses, forced values, and device replacement. This is not work that should be postponed until the end of configuration. The most valuable early decision is to build representative displays before mass production. Create an overview, a process area display, a rotating equipment display, a control loop display, a sequence display, a package interface, and a failure scenario. Put operators in front of them. Ask them to trace flows, find alarms, identify bad data, locate failed permissives, and transfer control. Watch where they hesitate. Hesitation is design information. A process graphic can look excellent in a presentation and still fail in a control room. Site testing must consider normal viewing distance, control room lighting, multiple monitors, alarm banners, fatigue, and the pressure of real operation. The final question is not whether the display looks modern. The final question is whether the operator can understand the truth immediately. When the plant is stable, almost any display appears acceptable. The true quality of the design emerges when the transmitter fails, the compressor trips, the controller saturates, the valve sticks, the communication link disappears, or the sequence stops halfway. At that moment, the operator does not need artistic sophistication. The operator needs clarity, consistency, trustworthy data, and an obvious path to action. That is why standardized process graphics are not merely drafting conventions. They are control system engineering, human factors engineering, and operational risk management expressed through a common visual language. Look at the displays in your own project and ask yourself 3 uncomfortable questions. Can an operator distinguish command from actual state? Can an operator recognize invalid data before acting on it? Can an operator understand what remains available after the primary control path fails? If the answer is unclear, the graphic is not finished. Share your experience in the comments. Tell me where inconsistent symbols, colors, alarms, package graphics, or hidden logic have created real operating problems, and tell me which human-machine interface design rule you consider non-negotiable. Like this episode, share it with your engineering and an operations network, and subscribe to the channel for more technically grounded discussions on engineering design, automation, standards, project execution, and plant lifecycle performance. Follow my LinkedIn newsletter for deeper engineering design and management guidance, and get in touch when you want to examine how these principles can be applied to your control system philosophy, project specifications, design reviews, factory acceptance testing, and operational readiness.